can't. But it is. It's paradoxical, and yet it works.
Hello there, so student connects 4 lamps ABCD in the circuit shown in figure 1. Battery has an EMF of 9 volts. Okay, so you got table shows the operating conditions when they're at normal brightness. So you've got the voltage and you've got the power. So student observes 2 of the lamps are at their normal brightness. Assume that any change, So determine which 2 lamps are at their normal brightness. So which 2 are working properly. So what you've got, if you to redraw this, you've got 2 resistors, A and B, in parallel with C and D, and that is in parallel with the power supply, so 9 volts. So that means the voltage across any one of these branches is 9 volts. So do we know the resistance of any of the resistors? Yes, we do. So we got V and we got P. Can we work out R? So yeah, power is V squared over R, or R is V squared over P. Oops. Okay, so if you used to do it for A, which is equal to C, we just do P, 6 squared over 6. Okay, so if you just put that into your calculator, that should be pretty straightforward. So that would just give you 6 ohms. So I know A is 6 ohms, and I also know C is 6 ohms. And then if we do the same for B and D, R now is V squared over P, which in this case is 3.5 squared over 4.1. Now if you put that in your calculator, and just give me a second. Okay, so that gives you 3 ohms. So we now know that is 3 ohms, and that is 3 ohms. Okay, so now you can do a number of things here. So you can actually work out the current in each branch. Okay, now the current in each branch, you could just do V over R. So the total R in each branch is 9 ohms, and the total voltage in each branch is 9 ohms. So you can work out the current, and then you can do V equals IR individually. Or you could just use the potential divider, isn't it? So if you look at the top branch, the total resistance is 9 ohms. 6 is 2/3 of 9 ohms. So 6 takes, the 6 ohm resistor takes 6 volts. That takes 3 volts. And you can do the same for the bottom. 6 ohms, again, is 2/3 of 9 ohms, which is the total resistance. So therefore, the voltage across here is just use the potential divider argument. So that must be 6 volts, and that must be 3 volts. Okay, so let me just label these A, B, C, D. So the A and C require 6 volts. So A and C are working normally, aren't they? A and C are working normally. Okay, and B and D, they require 3.5 volts, but they're only getting 3 volts. So B and D are not at normal brightness. Okay, so if you look at what you put there, you sort of got, you pretty much got it. So that's good. Okay, second part of this question. So now what they've done, they've put a bulb in between. So it's identical to A and C. So it has a resistance of 6 ohms. Explain what the student would observe regarding the brightness of the lamp. So refer to PDs across E in your answer. So yeah, so what do we know? A has a PD of 6 volts and C has a PD of 6 volts. So therefore, what's the potential difference at those 2 points? It's 6 volts minus 6 volts. So the PD of E is 0 volts. So 0 volts doesn't lose any energy there. So the PD across, so what you wrote, so the PD across E is 0, or there is no current flowing through. Brilliant. So adding lamp E has no effect. Yeah, brilliant. Well done. Okay, so lamp B in figure 2 fails so that it no longer conducts. The change does not affect the resistance of the other lamps. deduce the effects on the current in the battery. So in order to do that, we need to work out the current before, which we didn't do. So before now I'm going to go through every step. You don't have to. You just have to sort of visualize this in your head. So you don't have to draw this out. I'm just drawing it out so you can see what you should be thinking. Okay, so that's 6 ohms, that's 3 ohms. Now, what is that the equivalent of? So you can neaten up the top. Well, you got a 6 and a 3, so that's 9. And you've got a 9 at the bottom. Okay, and then, well, what's the total resistance here? Well, if you get two identical resistors in parallel, you just do one of them divided by the number of resistors. So in this case, 9/2, so that's 4.5 ohms. And across that, you've got 9 volts. So we can work out the current in the original circuit is V over R. You go to formula, so that's 9 over 4.5, which is 2 amps. So that's the original situation. Now, B doesn't work anymore. So what we got A, E, and you've got C, okay, and then you've got that connected to D. Right, so we've got to now work out the current of this. So as I said before, Ziad, pretend you're an electron. What can you do? You've got a choice here. So you've got a choice there. So you can either go up this way, okay, and then through there. Or you could go here and then go down through there and then through there. So if you think about it, let me do the top one first. You have now got, in fact, I'll just do it all together. So you've got a choice. You go either up through A and E, or you go through C as an electron, and then you will both then go through D. Okay, so that's 6 ohms, that's 6 ohms, that's 6 ohms, and that's 3 ohms, I think it was. Okay, so can you see, pretend you're an electron, what can you do? All right, I can go the blue route or I can go the green route. So let's neaten this up then. So and again, I'm going through too many steps. You should be able to do this anyway. So that's 12 ohms, and that's 6 ohms. Okay, so we've got a parallel bit in series with your 3 ohms. Now, 12, for the parallel bit, 1 over 12, 1 over 6, plus 1 over 6 is 1 over RT, or just do product over sum. Okay, so if I do product over sum, so 12 times 6, and then divided by 18, so that gives me 4. So that's the equivalent of having a 4 ohm with your 3 ohm. So that's the total resistance of, you can do the maths, I'm sure, 7 ohms, and you've got 9 volts across it. So what's the new current? V over R. So it's 9 over 7. So clearly the current's going to 9 divided by 7. So that's 1.29 amps. So can you see? So you do see effects on the current, and the current decreases because because the total resistance increases. Hopefully that helps.